When I took real analysis my very first semester in my PhD program, we didn't really know how we were going to be graded at first, but we quickly found out that there were no tests in that class, but we ended up having to do homework problems and then present those problems at the board for credit. So the very first set of homework problems he gave 6, and they were built in a way where it progressively got harder. So problem number 1 was easy, 2 was a little bit harder, 3 a little bit harder than that, 4, 5, and 6. And problem number 6 was by far and away the toughest one of those original 6 problems he gave us. Problem number 1 was like prove the closed ball is closed or something like that, which I did on this in an old video. But problem 6 was notoriously difficult. And I remember doing those 6 problems, and I could do 1, 2, and 3. 4 required a lot of help. 5 I was not really able to do, but I could write something down and like get to a certain point and then get stuck. And then number 6, I didn't even know how to start. And for a long time, no one in the class did number 6 up at the board. Until this one kid in the class, his name was Patrick. And Patrick solved problem number 6 in the class. And so me personally, I thought number 6 was the hardest problem that, at least at the time, it was the hardest real analysis problem I've ever been given. There have since been tougher problems, but that one at the time was the toughest. So whenever I think back on the tough problems I had over the past 2 years, I always think back to the Patrick problem, and that's what I've kind of been calling it, whenever I look over my notes. I don't really look over this problem too much, because I don't think it's useful to study, but I look at it every time I flip through my notes. Anyway, I thought I would show it to you on the channel now. So what does the Patrick problem say? Let sigma be a bijection from the natural numbers to the natural numbers. And we want to prove that the 2 statements are equivalent. The first statement says that if I have a series that converges, where an is some sequence, then the sum of a sigma sub n also converges. So what does that say? It says that if I add a1 to a2 to a3 to a4 to a5 and so on and so forth, if that converges, then I know that if I rearrange the terms, that series still converges. Okay. So that's the first statement. And then the next statement says, there exists an M such that for all n, the image of this index set can be represented as a union of at most m intervals of consecutive integers. So it's important to talk about this word interval. It's not like the usual interval that we're familiar with, the set of all numbers between 2 given numbers. We're only talking about integers here. So if I wrote down an interval notation like 1, 10, that would be just a set of integers from 1 to 10. It's not like fractions and decimals and whatnot. So this is the statement. So the problem is you have to show this implies this and this implies that. And this problem actually has a name. It's called the Riemann rearrangement theorem, if you're interested in looking it up. Because when Patrick proved this up at the board, he wrote a lot of things down, but sometimes he would just tell us something and then not write it down, which made copying it down kind of difficult. So I tried my best to recreate the argument, but there still might be some holes in it. But 90% of it is here, if you're interested. And if you want to check it, you can look it up. It's the Riemann rearrangement theorem. And what's actually funny is that one night I was just looking at some PhD Harvard mathematics qualifying exams just to see what the boys at Harvard are doing. And from it was either 2001 or 2002, they had a qualifying exam problem, and sure enough, this was on that test, which makes me think my professor actually got it from that test when he was picking 6 problems for us. It's not an easy problem. safe to say. Okay, so I've written it up here, so let's just go through it. Assume that we have the first bullet point. So that's what I've written here. And the idea is that we're going to proceed by contradiction. So we write down the contrapositive, or whatever it is, the negation of this statement. We assume that for any m, there exists a capital N. And I don't know why I wrote capital N. It should be lowercase n. Already making mistakes. There. Such that this image can be represented by at least m intervals of consecutive integers. And then we proceed by a construction. So how do we do this? We're going to set x sub 0 to be equal to 1, and then we're going to let y naught be the maximum of this image of integers. So you take all these integers where you count from 1 to x0, you look at the image of that set, so it gets you more integers, and then y naught is going to be the maximum of that set. And we're going to call that sigma 1. All right, what now? Next, we're going to choose x1 so large that this interval of consecutive integers is a subset of this guy, which is possible because we can always choose a bigger integer. And then what else do we need? We need that the image of this set is at least one interval, which we can do because we assumed that we could do something like that. Horrible. Forgot my parenthesis. And now we proceed in a similar manner. So now we're going to let y1 be the maximum of this set. And unfortunately, I've written it not in a good way, because I'm setting it equal to the maximum sigma of this interval, which ends at x2 here, and I haven't defined x2, which I do over here, so it's a little bit out of order. So I would rewrite this, or I would put this part here, like right over here or something like that. Choose x2 so large that the image of this interval is equal to this guy. So this one depends on y1, which we already defined up here somewhere. Where is y1? Wait, that makes no sense. We've already defined this one to be that. Hold on, let's see here. I may have written something down here that needs fixed. Y naught is equal to max of that. That makes sense. X1 so large, then that sets inside. That makes sense. Choose at least one interval. I think this 2 needs to be a 1 here. I think that makes more sense. And then we choose x2 so large that we have this property. Okay. Double check me on that. I think I corrected it, but it's a little bit, makes me a little bit queasy. All right, and then we want this image to be at least 2 intervals, because remember, we're proceeding by contradiction up here. Okay, so now the idea is that we're going to repeat this process to get a sequence of x1s and y1s, or not x1s, but xk's and yk's. Okay, so set y2 to be that maximum, continue this process for yk. So in general, we'll have this condition. We have the set of integers from 1 to xk to be a subset of 1 to yk minus 1, and yk is set to be the maximum of that image, the biggest integer in that image. What does this mean? It means that we can partition our natural numbers into intervals of consecutive integers. And we denote these intervals as ik. So ik is the set of all integers n between yk and yk plus 1. All right, now what we're going to do is we're going to define a sequence an. And this sequence an is going to have a property that's going to violate our original assumption. We're going to have sum of an as n greater than or equal to 1 converges, but the sum of a sigma n is going to diverge. So how do we do it? We let n be an element of ik, so it's somewhere in here, and we consider this image, and then we're going to define for every n, the term an is going to be equal to -1 to the k over k. And remember, this n is in ik. So that's how these two are related. Oh, sorry. This an is going to be equal to this if it's in the interval, but not in this image. And then we're going to let an be equal to a similar term, except we're going to add 1 to the k, so the sign changes. So we're constructing an alternating sequence. And this is going to be satisfied if n is in the image. So if n is in this image, it's equal to this guy. If n is not in the image, but still in the interval, then it's going to be equal to this guy. So we get an alternating sequence. And now what we're going to do is show that the sequence converges. So we let epsilon be given, choose a natural number, so big, so that n is in this interval. So just as a clarification, this represents the ceiling of 2 divided by epsilon plus 1. So we add 1 to epsilon, we take 2 and divide by that number, and then we take the smallest integer larger than that number. That's the definition of ceiling. You can see here that this is not at all obvious because, I mean, how he was able to come up with this solution, I don't know. Maybe he found it on the internet somewhere. I mean, it took him quite a while to present this, but safe to say I probably would not have, well, not even probably, I definitely couldn't come up with this. Now, if n1 and n2 are bigger than n, we consider this sum, so we run from n minus 1 to n sub 1 to n sub 2, which gives us this sequence, and that's supposed to be less than ai plus aj, or some aj and ik. I'm not entirely sure what is meant by this, because we talk about aj, but we don't really talk about ai. I understand that it's some term in the sequence, and we can, I mean, it's a finite sequence, it's positive, so we can bound it above by something. But I'm not entirely sure how we're picking a1 here, or ai. That part didn't make it into the notes. But aj is in ik. And we know that 1 over k is less than epsilon over 2. Oh, because remember, we're defining these a's to look like this and this. Okay. So what does that mean? It means that k is larger than 2 over epsilon. That part I understand. Even I can do that part because of this. And so this means that the sum converges. Because why? Because this is a Cauchy sequence of, I think that's true. I think because this sum is Cauchy, then if Cauchy, then convergent. So he didn't show it was convergent directly. He showed that it was a Cauchy sequence, more or less, or a Cauchy series. I'm not sure how you want to describe it. But you can talk about the convergence of a sum by redefining is it a sequence of partial sums, which I think is the idea here. Is written in a strange way, and I'm still unsure about what's going on here. But I think I see something meaningful here. I'm going to be honest with you. I don't like this problem. Okay. So given n1, we can pick an xk larger than n. And now we're going to consider the series of a sigma n for n larger than or equal to 1. And this series should simplify a bit when you expand it out. to get you something that looks like this. So these are my alternating sequences. I think I skipped a lot of intermediary steps when I go from here to here, because in my notebook, space was precious. So I believe when he did this at the board, he actually expanded this out and then simplified it a lot. And then I left those details out when I rewrote it, because I think it was just a bunch of algebra. As long as, I could see like the end result, I was content enough to write that in my notepad. So in general, when you do a problem like this, you should not skip those details. But I do remember this because, this problem has taken up 3 pages so far, and it took even longer to do at the board, I remember. But this should simplify to this. And then it's not hard to show that when you simplify this algebraically, you get it equal to 2 here. And that's where our big fat contradiction lies. Because it's not getting smaller, this series has to diverge by the Cauchy criterion test. And that gives the contradiction. So because we violated our original assumption, we know that our presupposition was wrong, so everything's good. That's one direction, so we still have to do the other direction, and thankfully, the other direction is a lot shorter. Okay, conversely, assume there exists an m such that for all little n, the image of those integers can be represented as a union of at most m intervals of consecutive integers. All I did was rewrite the assumption. I do that a lot when I prove stuff like this. Well, when I copy down other people's proofs like this, we'll put it that way. So now we want to assume that this series converges, and we want to show that A sigma n converges. That series converges. So we let our epsilon be positive. We choose a C positive so large that N1 and N2 are bigger than C. And we have that this quality holds. The sum from N1 to N2 of AN is less than epsilon over 2 to the M. And that's doable because we know the series converges. And now what we want to do is choose our M so large that for sigma n, it's larger than C. So remember, M is the union of these guys of at most M intervals. So we choose a big enough M such that this sigma is larger than C. Man, I don't like that. What does sigma n have to do with C? Choose M so large that sigma n is larger than C. I don't know, man. That's weird. N1 and N2 are given. For any n larger than big N, we have this sum is equal to these partial sums, because we can partition it, right? I think that was one of the statements that we said. We could partition it into consecutive intervals I1, I2, I3, all the way up to I2M. So, okay, that part I'm happy with, because this is just a big string of intervals, and then you can choose it so large that I can split up the sum into partial sums, and then I just apply a triangle inequality here. And then by using this assumption, this gives me a finite geometric series converging to a number less than epsilon. And so by the similar Cauchy test, because this quote-unquote Cauchy series less than epsilon means that my series has to converge. That part I'm okay with. It's just when I see stuff like this here, it makes me uneasy, because I don't really see what sigma n has to do with capital C. I think it just means that we can get this finite partial sum, or series of partial sums. Come on, man, say it in the right way. This finite series of partial sums. Anyway, that's more or less it. I hope there weren't too many details left out. It has been a long time since I've seen this problem, and I don't really know where to find it on the internet. I only recently discovered it was called the Riemann rearrangement theorem, but I've never read it in any textbook. I haven't really... I found it in a very obscure place, too. It was from a 2002 real analysis call at Harvard in their archives. You can find it on the internet. I think it was 2002. It may have been 2001, somewhere way back there. But it is kind of a headache of a problem, and it's not something that we usually do in class, so I haven't really studied it that much. But I did have stuff written down for it from when we did it back in the day. It's just that some of those details didn't make it up at the chalkboard, so it was hard for me to recreate the argument here. But if anyone found it remotely interesting, I hope you did. Anyway, so I'll do more problems in the future, probably continue the real analysis episode series, whatever I called it, make some more problems. I've been kind of swamped lately, as people tested me. So, but don't worry, we will return with more problem-solving videos in the future.